So we saw that the probability of at least one can get really tricky. So it pays to actually do some more examples just to kind of set it in our brain what the heck we're doing, because it can get so complicated and confusing. So here we have the table that shows the graduates from JC by degree. We've seen this table many times. You're going to select two JC graduates. So there's something to pay attention to, because you know the number of trials you're looking at is 2. What is the probability that at least one of them, okay, so we know we're doing an at least one problem, was a certificate? All right, so we're interested in at least one certificate. So event E is going to be certificate, and I need to find the probability of event E and the probability of its complement. Well, event E is not hard to figure. It's right here in the middle of our table, right? It's the certificate group. All right, so there's certificate. And then the complement of that is everything that's not that, because of course the sum is 1 for all these numbers. So we would take 1 minus that. All right, there we have it. One student. Event E is certificate. Event not E is not certificate. All right, so now what about 2 students? For 2 students, we want the probability of at least one certificate. So we're going to find the probability of no certificates for both, and then no certificates at all. So we're going to take the probability of no certificate and raise it to the 2 power. All right, so the number of trials is 2, so that's why I'm raising it to the 2 power. I'm interested in at least one certificate, right? That's my event E. So I'm going to take the probability of not getting event E and raising it to the 2. Okay, but not getting event E would be 1 minus. All right, well, we already found what not getting a certificate was. It was 0.7883 right here. So we're going to take that 0.7883 and we're going to square it because we're dealing with 2 trials. So that would be 1 minus, and now I've got to grab my calculator, 0.7883 squared would be 0.6214. Roughly. 1 minus that would be 0.3785. Of course, we're rounding here, so I should put in the squiggly approximation equals. But other than that, we're good. Done. All right, great. So now let's do one more example just to make sure we've got it cemented in our brains. We're going to select 3 cards at random from a standard shuffled poker deck with replacement after each draw. Now, why do we do with replacement? With replacement is to ensure that the independent rule, the multiplication rule for independent events applies. So that's all that's about. So let me make a little note. So then they ask, what is the probability of at least one, there's those magic words, spade. So our event that we're interested in is a spade. All right, so let's figure out for single cards first, just like we've been doing, right? And then we'll kind of go from there for more cards. So a single card, the probability of a spade, which is event E, right? It's saying right there, at least one spade, so event E is a spade. So the probability of that is 1/4. A fourth of the deck is spades. So then not E would be equal to not a spade, which would be 1 minus a fourth, which is 3/4. So that's the probability of event E and event not E. In particular, we want to use the not E, the 3/4, because that's what we're going to raise to the power. But let's do that. So I made this little note right here. I think I'll just move that note down so it's a little bit easier to spot. Okay, so now we're going to look at 3 cards. So for 3 cards, the probability of at least one is 1 minus the probability of not to the 3rd power, because we're looking at a trial of 3. So let me type that up. Okay, so the probability of at least one spade, like I just said, is 1 minus the probability of not getting a spade to the 3rd power. But we already figured out the probability of not getting a spade in one draw. It's 3/4. And then we just raised to the 3rd power to get the 3 cards that we're talking about. Oh, well, that would be 1 minus 27, because 3 to the 3rd is 27, and then 4 to the 3rd is 64. So that'd be 1 minus 27 over 64, which would be 37 over 64. If you don't believe me, 1 minus 3 over 4 to the third power. There we go. If I go math 1, it tells me it's 37 over 64. See? And that's an approximation of 0.57. Actually, I don't even need approximation. It's 0.578125. And there we have it. All right, so these are the answers. Again, we're taking the probability of ones first, one trial, figuring that out, and then we're using that probability down here for 3 trials. In particular, we're using the probability of not E and then raising it to the, or not spade, not E, and then raising it to the third power and then subtracting from 1. Moving on to the last example in Chapter 5, we want to look at dice for craps. So craps is a very common gambling game you can find in most casinos. So you're going to play 3 rounds. Oh, better pay attention to that because it's telling you what your sample size is, your experiment size is. So you're going to go 3 rounds of craps. And craps is when you take 2 fair 6-sided dice and you throw them and then you sum them, so you add them up. Now remember, we've already found the probabilities for adding 2 6-sided dice. We did it a while ago in section 5.2 or 5.3. No, 5.2. So we've already found this, and it's also currently in the exam notes packet. So 2 6-sided dice is right here. So there's the sums over on the left, and there's the respective probabilities. So I could just paste those right in here, and hopefully it'll work. Beautiful. So in this example, we're going to do a few different types of things that we've done along the way just to remind ourselves how to do them. So the first one is, what is the probability that the first roll is a 5, the next roll is a 6, and the third roll is a 7? Okay, so you want first one thing, then the next thing, then the next thing. So we want the probability of a 5 multiplied, and so you'll see the and is right there. So we're going to multiply these probabilities. Right? So I'm going to take the probability of the first one being a 5, and I'm going to multiply it by the probability of the next one being a 6, and then multiply it by the next one being a 7. But the probability of 5 is 4 out of 36, the probability of 6 is 5 out of 36, and the probability of 7 is 6 out of 36. And that would give me 120 over 46,056. I can prove it, 656, excuse me. I did that by doing the numerator and denominator separately. 4 times 5 times 6, and so on, and then 36 to the third. Now, if you do it in the calculator, you can actually get the reduced fraction if you so desire. So you can make the calculator give that to you. So I'll find the decimal first, and then I hit math 1. I mean, technically you can do it all at one step, and it'd be 5 over 1994. So I'll just throw that in as well. So it's 5 over 1944, just in case you're interested in a simplified fraction for some reason. Although in general we don't care that much in probability. Not for what we're doing. All right, so that was a review of the multiplication rule. And actually, since it was for lots of events, it was multiplication rule, let's see here, scrolling through the table. It was number 5, right? Because we had more than 2 events. So this is rule number 5. I'll make a little note. All right, so it was rule number 5 that we were reviewing for that one. Now, what's the probability that all 3 rolls are 8s? There's that word all. That's a keeper, right? All is another hidden and. This is actually going to be another multiplication rule problem, right? It's just that the multiplication is even easier than it was on the last one because everything's going to be the same. First I want an 8, then I want an 8, and then after that, wait a minute, let me think, I want an 8. So I want an 8 for every single one of them. Therefore, it's going to be quite simple. So it's first an 8, and then the second is an 8, the second sum, and the third one's an 8. So that's the probability of 8 times 8 times 8, which is probability of 8 to the third power. Okay, so the probability of an 8 is 5 out of 36. So I'm going to take 5 out of 36. Oh no, it's 6 out of 36, I'm sorry. check myself on the table here. Nope, it was 5 out of 36. I did it right. Yeah, it's 5 out of 36. So I'm going to take the probability, which is 5 out of 36, and I'm going to raise it to the third power. So the probability of 8, I'm going to raise it to the third power, and that would be taking 5 out of 36 and raising it to the third power. And that would be 125, actually, divided by 46656. Which, let's see, 125 divided by 46656 would reduce to 0.002679, and the fraction would reduce to nothing. Doesn't reduce. It just is what it is. Okay, then. And we're done for that one. So that's another review of the multiplication rule. All right, so next, what is the probability that none of the rolls are 9 nor 10? Oh, well, that's a little bit of a tricky one. So we're kind of using rule number 5, but we're also kind of using the fact that we want neither 9 nor 10. So we got to be a little bit careful about how we build what these probabilities are. Okay, so let me just think about a single roll. What's the chances of a 9 or a 10 on a single roll? Well, a single roll would be just one toss of the dice. One toss of the dice. So a 9 or a 10 would be an or, so it's an addition rule problem. So I'm actually using the addition rule for that part. And then I want to add it up. So I want to say, okay, 9 or 10, that's 4 out of 36 plus 3 out of 36. That makes 7 out of 36 for a 9 or 10. So not getting a 9 or 10 is the complement of that. So I'm using the complement rule as well. So a not 9 or 10 is 1 minus that. Okay, so complement rule and addition rule so far. It's actually the disjoint addition rule because, of course, when you toss a set of dice, they can either be a 9 or a 10, but they can't be both. So it's actually rule number 1. And then you're also using the complement rule, which is rule number 3. Okay, so now I want to take those numbers and I want to use them for 3 rolls. So I want to say, okay, so when I toss it 3 times, what's the chances that none of the rolls are 9 nor 10? Okay, so I want the first roll to not be a 9 or 10. I want the second roll to not be a 9 or 10. And I want the third roll to not be a 9 or 10. So that's the probability of not 9 or 10 times itself 3 times because there's an and in there. So that's the probability of not 9 or 10 to the third power. But we already found the probability of not 9 or 10. The probability of not 9 or 10 is 29 over 36. So I'm going to take 29 over 36 to the third power. So I just need a calculator to find out what the heck 29 to the third is, because that'll be my numerator. I already know the denominator because it's the same denominator we've had for every one of these. So it's 24389. So over here. All right, and then if I divide that with a calculator, I will get 0.522741. If you don't believe me, there's the calculator right there. All right, so we're done with that one. So that was actually a combo. We had to kind of use the disjoint rule, the complement rule, and the multiplication rule all to get what we wanted, which was the probability of not 9 or 10 to the third power. All right, last but not least, we want the probability of at least 1. All right, that'll be problematic because these are always the trickiest ones. I want the probability of at least 1 7. So again, for a single toss, a single roll of the dice, the probability of event E is obviously a 7, is the 6 over 36. So not E is equal to not 7, which is 1 minus 6 over 36, which would be 30 over 36. All right, again, that's not what I was looking for, but it's just going to help me because now this is where the fun begins. So if I want the probability of at least 1 7, I want to take the probability of not getting 7 and I want to raise it to my n power and then subtract from 1. It's still the third power, of course, because it's still 3 tosses of the dice. So I'm going to take the probability of not 7 and raise it to the third power. But we already know the probability of not 7 because we've already found it. It's 1 minus, and then not 7 was 30 over 36. So I'm going to take 30 over 36 and raise it to the third power. Okay, well then we know what our denominator is going to be because it's been 4, 6, 6, 5, 6 for every one of these. It's just a question of what is 30 cubed. So 1 minus 30 cubed, which should be 27,000 if I'm not mistaken. So let me show it to you. 30 cubed. Yep, 27,000. Now that would be 19656. Just doing the subtraction there. Divided by 46656. Okay, so, and if you don't believe me, 46656 take away 27,000. Sure enough, it's that number divided by 46656, just so I can get a decimal, and it's about 421296. And there we have it. So that was a review in that example of the multiplication rule, the complement rule, the at least one rule was what we were just reviewing on this last one. Which, of course, when you do the at least one rule, you're actually doing multiplication rules and complement rules kind of as you go. In particular, when you figure out the single rule business up here, you're really doing the complement rule. And when you figure out the 3 rule business down here, you're doing the at least one rule, which technically involves the multiplication rule, because you can see we're raising something to the third power.